So welcome everyone. We're actually in the last week of the class. So kind of, I mean, there's next week too. So, but next week is finals week, and we have some stuff and some not stuff, presentation day, final, that kind of stuff. I still haven't heard back from the dean. Maybe they're too busy. I don't know. I didn't say anything bad or anything, so they shouldn't not like me or anything. So I'm not sure what happened, but I'll let you know as soon as I can whether next Wednesday we'll do an in-person thing or not. So we'll see. Again, I don't get to choose. All I do is ask. So let me share my desktop and I can talk about what we're doing today. Okay, so here's the plan and the schedule. What we'll do is we will start out with Q&A as always. So happy to answer any questions about homework problems or whatever else you might be working on. And then we're going to move on to what we were doing before, except now we're doing it in that abstract form. But it's a really important day, although I've kind of talked about it already, just because it's just hard to resist. It's so amazing. And that is that we're going to be talking about linear transformations. And we saw linear transformations, 4 weeks ago or something like that. And the definition is exactly the same. The only difference is it's not talking about a bunch of numbers with commas in between. It's talking about vector spaces. And these could be general things. So then we'll get into the properties of linear transformations. And then we'll talk about spanning sets, bases, and linear transformation. And then we'll move on to what we've already done. So again, this is all review, except it's review in a way we haven't thought of before, possibly. And that is, what is a one-to-one linear transformation? And what is an onto linear transformation? And as you might guess, definition is exactly the same as what it was before. The only difference is now our perspective is wider. Then we'll talk about what an isomorphism is. So again, same thing, no different, but our perspective is different. And then we'll talk about, well, what if we have two linear transformations and we want to compose the two linear transformations? And the nice thing is you already know how to do that because linear transformations are functions. And it's no different than composition of functions. And then we're going to get into if you have two vector spaces. So for example, P3 and M2 by 2, right? I mean, when you think about it, does a third degree polynomial and a 2 by 2 matrix have anything to do with each other? What do you think? Or are they like, I don't know, just different stuff? Any thoughts? You're all being quiet. Hopefully you can hear me.
Isn't the vector space of a 2 by 2 matrix in the third dimension?
Nope. No, it's in the fourth dimension. It's in the fourth dimension. So it turns out they seem to look nothing like each other. Like 3x squared plus 5x, sorry, 3x cubed plus 4x squared plus 2x plus 7 versus the matrix 1, 4, 2, 7. And it turns out they're actually exactly the same things, even though they don't feel like it. But we're going to show that they are isomorphic to each other. And once they're isomorphic to each other, one is the same as the other if you look at it in the right perspective. And so we're going to be talking about isomorphic vector spaces. So there's some really weird stuff that goes on with that. Because again, you can realize that polynomials of even degree, polynomials are matrices. I know you've probably never even thought about that, but they are. And we'll talk about that. Okay, so that is the plan of the day. Just a reminder, what happens a week from today?
The final.
Definitely not the final.
Presentations.
Presentations. Yeah, presentations are a week from today. So a week from today, you're gonna be doing your presentations. Everyone have a partner?
Just not me.
Okay, can anyone grab Jordan? Remember, a group of 2 is allowed to be a group of 3 as long as there's only one group of 3. So I think everyone else is a group of 2.
Jordan can join us. Me and Jason.
Did you hear about
Okay,
that?
cool.
Okay, so everyone else have a partner? Hopefully. And again, remember, you know, you posted, some of you posted your ideas, and it's first come, first serve. You're not allowed to do, you can't have 2 groups doing the same thing because that's redundant. So the idea is everyone should have a different topic. And I listed a whole bunch of possible topics, and there's a lot more too. I just listed the ones that, you know, I found quickly, or the ones that I wrote.
Wait,
And
where can we post our what we want our topic to be?
Chat box?
Oh, chat box. Okay.
Yeah, because everyone can see it. Yep. And it's private. Remember, the chat box doesn't get YouTubed. So if you're worried about privacy, which you shouldn't, but if you were, then you know it's private. So anyhow, what's the difference between the presentation and the special application? That's the same thing. If it looks like there's 2 assignments on Canvas, I'll have to check. Could be that they got duplicated, but there's only one presentation. Yeah, so I'll take a look. But either way, you should take them seriously. Take the presentation seriously. Then a week from Wednesday is a maybe. I don't know about whether we'll be able to do an in-person thing, but if we can't, we can't. But I'll let you know, hopefully by this Wednesday. That'll give you a week in advance. And then a week from Friday is the final exam. Yeah, the final exam is a week from Friday. So, you know, start getting ready for it. Just let you know the final exam is comprehensive. But the good news is everything we've been doing lately really is reviewing the old stuff too. Have you noticed that? All these words that we got on the list today, you've seen all these words. So the nice thing is that this week is kind of a review week anyway. But the final exam is comprehensive. So, you know, you're responsible for anything that we've already done is the plan. Any questions? Could be homework questions or other questions. Any questions?
Can we do number 3 on 9.5?
Is that the one in the book or is that the handout?
The handout.
The handout. Oh, good. So the nice thing about the handout is I prepared. See, the handout's a Word document. I don't know if you realize that, which means all I have to do whoops, just a minute. I lost my Word document. There it is scroll down because I put that in knowing that there might be some questions. Okay, so number 3 is here. And that is let V be the vector space of P3 and U be the subspace of V consisting of all polynomials of degree 3 or less that are solutions to the differential equation y double prime minus y equals 0. Okay, let W be the subspace of V consisting of all polynomials of degree 3 or less that are solutions to this differential equation y double prime minus 6y equals 0. Okay, find the dimension of U plus W and the dimension of U intersection W. Okay, so what do you have to do?
Find the dimension.
Yeah, we have to find the dimension. How do we do that? So what do we have to do to find the dimension?
Find a basis.
Yeah, so we can try and find a basis. Okay, and y double prime minus y equals 0. So again, this involves a little calculus. Okay, if you want to do it with calculus. So do you remember how to do it? It's been a while since you actually did any calculus, but this is a nice review. This is to get you ready for next quarter, by the way. So y double prime minus y equals 0. Do you remember how to solve that?
Not really.
Okay, so we know that the second derivative of a function, so let me take this, copy it, and rewrite it. So we know the second derivative of y is equal to y. Hopefully that was not a magical step, was it?
No.
Okay, good, good. So can you think of a function where you take two derivatives and you get back where you started?
E to the x.
Good, good. So one is e to the x. Yep. I wonder if there's a typo here. I got to go into insert. This might be too easy. Okay, but that's not a polynomial, is it?
No.
Okay, if you take two derivatives and you get back where you started and you had a polynomial, because that's what we're looking at, then what must that function be? Because e to the x doesn't work because that's not a polynomial. So in a way, there's a bit of a trick question.
Any trig function?
Yeah, is a trig function a polynomial?
Can be.
You tell me what trig function is a polynomial. Because I've never heard of one. Yeah, trig functions can't be polynomials. Any thoughts? Turns out the only solution to this that's a polynomial is 0. Do you understand that? Do you believe that 0 double prime minus 0 equals 0?
Yeah.
Yeah. So in this case, y must be 0. Okay. Now, how about the other one? If you take a polynomial and you take two derivatives, and you get 6 times that polynomial?
It's the same. It's the same as the first one. There's no.
Exactly. So either way, you get y equals 0. Okay. So notice, now let me read this. V is P3. So U and W are both just a 0 set. Right? So what's the dimension of U plus W?
0.
Yep. What's the dimension of U intersection W?
0 as well.
Yep. So the dimension of U intersection W is also 0. So that's a little tricky because there's nothing there. It's a little too easy. Any questions on that? Okay. Other questions? If not, then I'll move on to the new stuff. Okay, let's do new material. And just a second. There we go. Okay, so hopefully you all remember. If not, you need to remember for the final exam this definition that we've already had. This is no different than the definition of linear transformation that we had, a month or so back. But let me reread it. And this is just literally, it's a copy and paste from what we did before. And that is T is a linear transformation from a vector space V to a vector space W if T of V plus W equals T of V plus T of W, and T of KV equals KT of V. Do you remember that? I'm hoping this looks more than familiar. You just remember it. Okay. And the book actually writes it in one sentence, but I like doing it in two because it's easier. If you have to prove something linear transformation, it's a lot easier to do 1 and 2 than to try and do all this at once. But notice that T of AV plus BW must be AT of V plus BT of W. And that's equivalent to both 1 and 2 combined. And notice it's equivalent because if A and so I've asked this before, see if you can remember again. Is there a way to take this OR piece and get number 1? How do you do it?
Multiply 1 over A.
Not quite. Yeah, that'll just be messy if we did that. Then you get 1 over A T of AV plus T BW equals T of V plus B over A T of W. I don't think that would help. It's a nice, easy thing.
We can do AB times DB plus WB.
No, it's easier than you're making it. All right, if no one's guessing it, let me tell you. Just let A and B be 1. Do you agree that just does it? So if A and B are 1, then you just have T of V plus W equals T of V plus T of W. And that's number 1. Okay, because this OR, that means for all A and B, this has to work. Okay, so now the question is, how do we go from this OR to number 2? Also easy.
Let T of W be 0.
Close, not T of W, because that's not going to do it, because then you'll end up with T of AV plus BW equals AT of V. But you can't have a plus BW, because number 2 doesn't have a plus BW. But you're on the right track. You just
Let B be 0.
Yeah, let B be 0 and maybe ABK, just change the letter of A. And then you get immediately number 2. So do you see that 1 and 2 combined is exactly the same thing as this bottom? 1 and 2 are easier to deal with and I think more useful. So the book does the bottom as their definition, but they're equivalent. Okay, so that's a linear transformation. And we've seen these before, right? If you had just vectors, good old, numbers with commas in the middle, then what do all linear transformations look like, basically?
They look like a matrix.
Yeah, they all look like a matrix. Okay, do you think the same is true for general vector spaces?
Yes.
You think so? Think
I think you
again.
can make them look like that, or at least most things.
Yeah, good luck. Good luck. So, yeah, you can't. So let's do the most things. Here's an example. It's the most important example. There's 2 kind of, they're tied. Let V and W be the vector space of differential functions. Okay. Any guess on what I'm going to let t be? So let t of v, let's call it f because they're functions now. You're more used to the letter f for functions. Equal? Any guess? Hint is these are differentiable functions.
F prime, bro.
F prime. Okay. So is that a linear transformation? How do you show it?
Show 1, 2.
Yep. So we got to show number 1 and number 2. Well, if we have t of f plus g, I'm going to use f and g because you're more used to those letters for functions, right? I mean, you can call v and w functions, but I like to call them f and g. Well, by definition, that's just f prime plus g prime. Oh, sorry, it's f, it's actually not. It's f plus g prime. But now we can use some calculus. What's f plus g prime?
F prime plus G prime.
Yep, that's f prime plus g prime. But f prime is equal to t of f by definition. And g prime is equal to t of g. So it works. So t of f plus g is t of f plus t of g. Any questions on that big statement? Any questions? Okay, well, now we get to number 2. Well, for number 2, what is t of kf? By definition, that's kf prime. Now, what does calculus say you can do when you have a constant times a function and you want to take a derivative?
Keep it there.
We can keep it there, but that's not what we want to do.
Just pull out that constant.
Yeah, you can pull out the constant. You can remove it. You can not delete it, but move it outside the parenthesis. That's k times f prime. But that is k times t of f. So there's the proof that the derivative is a linear transformation. Okay. Is the derivative of the space of for the space of all differential functions in the matrix? The answer is no. Okay. If you can come up with a matrix, good luck. You won't be able to. Okay. Any questions on that? Okay. What's the next most important thing we do in calculus?
We integrate.
Yeah. So there's example 2. Got to do these 2. These are the big examples. So again, now they don't have to be differential functions. Now they can be continuous functions or integrable functions. So let v and w be the vector space of integrable functions. Okay. And you learned at one point that if you have 2 functions that are integrable and you add them, they're still integrable. And if you multiply by a constant, you're still integrable, which means that you're a subspace of all functions. So this really is a vector space. Okay, and this one I need to write it with symbols. Let t of f equal the integral. This gets a little interesting. The integral from, and I'll let you pick a number. Give me a number. Any number, I don't care.
0.
0 it is. Okay. Any number you gave me, I can do this. To x of f of t dt. Okay. Why can't I just let it be just an indefinite integral?
Because of the plus c.
Yeah, the plus c, if you take t of f, you're not going to get a function, because when you do a plus c, it's no longer a function. So that's why we need to make it a definite integral. Now, any number down here would work, and it's fine. That's why I said, give me a number. If you gave me 20, that'd be fine too. Okay, well, how do we prove it?
1 and 2 again.
Exactly. It's nothing new here. I don't know why it keeps making it really in the middle. I wonder if I do that. Let's try that. Nope. I'll do Control Z. There we go. So number 1. So I'm going to copy and paste because it's easier. So t of f plus g is equal to the integral from 0 to x of f plus g of t dt. But that is equal to, we had a rule about integrals. Hopefully you remember, when you take an integral of a sum, what can you do?
Integrate both separately.
Yep. So we can integrate f of t dt. And then I can go plus, then I can integrate g of t dt, which I'll copy and paste and put a g in. But that's great, because the integral of f dt from 0 to x is equal to t of f. And the integral of g of t dt from 0 to x is t of g. Any questions? Any questions on number 1? Let's do number 2. And I think the easiest is to just copy and paste and change. So the integral of kf is the integral of kf dt. And then when you have a kf of t, that's the same thing as kf of t. And that is the same as k times the integral. I can always pull a k out, constants out, of f of t dt. And that's k dt, kt. Any questions on the proof that an integral, the integral, I should say, is a linear transformation? Any questions on that? Okay. Let's go into a different vector space. Let V be the vector space of, how about 2 by 2 matrices? And I'm going to say which of the following are LT, linear transformations. So the first is T of, let's call it A for matrix, equals determinant of A. The second is T of A. Actually, I should give it another letter. How about S of A is equal to A transpose. And how about another one? Third. Let's see, S and T we got. Let me get another letter. How about R of A is equal to the trace of A. Okay. So the question is, if that's our vector space, 2 by 2 matrices, which are linear transformations? I'm going to give you a moment, see if you can figure it out. If you can at least guess.
I think the determinant is not a linear transformation.
Okay. And how about the trace? Oh, sorry, the transpose and the trace.
I'm doing transpose right now, trying to prove it. I think it can be, but I don't think the trace can be, since it's just
Okay.
a number.
I think the transpose can be one because we're changing coordinates or something, but I don't think the trace can.
Okay. Well, let's see. All right. So first thing, everyone thought the determinant isn't, right? What do you think that? What's the easiest way? And we've done this a lot of times to show something isn't one.
Any example?
Yeah, let's just do an example. And I don't know. How about this one? Let's suppose that let's do number 1. Let A equal, okay. We don't want it to be a 0 matrix because that's boring, and that'll actually work with the determinant. What's the next easiest matrix after the 0 matrix?
The identity.
Yeah, let's let A be the identity. 1, 0, 0, 1. Okay. And let K equal, can't let it be 1. That's not going to do anything to it, right? So how about 2? Is that going to be a contradiction? Is that going to make it so it's not a linear transformation?
No.
Let's see. What is 2 times, actually, what is the determinant? I think I need to do it this way. Determinant of 2 times the matrix 0, 1, 1, 0, 0, 1. I guess I should put some parentheses around that. Well, let's just do it. What's 2 times 1, 0, 0, 1?
2, 0, 0, 2.
Uh-huh. And what's the determinant of 2, 0, 0, 2?
4.
4. Okay. On the other hand, the term 2 times the determinant of 1, 0, 0, 1, the identity, is what?
2.
That's 2. So what's the conclusion?
It's not a linear transformation.
Mm-hmm. T is not a linear transformation because T of KA was not K times T of A. Any questions on that? Okay. So let's go to number 2. So what do you think? Do you think it might be a linear transformation, or do you think it might not be?
I think it could be possible.
Okay.
Yeah.
So if you think you think it probably is, then we should go and prove it. Okay. So then what we can do is we need to take 2 matrices. So we're going to have S. Let's do it this way. S of, that's messy. So now a general matrix is A, B, C, D. Hopefully you all agree that covers all 2 by 2 matrices. And then plus, and then the next general matrix, just alphabetically, E, F, G, H. Okay. Well, that is equal to S of, let me borrow the matrix. We got to add those matrices. So we're going to have A plus E, B plus F, C plus G, D plus H. Stop me if you don't understand something. All right, what does S do to the matrix?
Transpose.
Takes the transpose. So let's take the transpose. So transpose switches the off diagonals. So that B plus F becomes a C plus G. And the C plus G becomes a B plus F. Anyone lost on that? Okay, so that's what S of these 2 matrices are. Now what we have to do is say, well, what is S of the first plus S of the second? I think I want to do it this way. So S of the first plus S of the second. So let's go and do it. So S takes the transpose, right? So ABCD becomes ACBD. And EFGH becomes EGFH. What happens when you add those matrices?
You get the same.
Yeah. So what we can do, I'll just copy and paste. I'm going to type it all. When you add those up, you get what you get what you wanted. We get A plus E, C plus G, B plus F, and D plus H. Okay, so that worked. Are we done?
No, we got one.
Yeah, we got one more, but unfortunately, it's not that hard one. So we're going to take S of K, ABCD. But that is equal to S of KA KB KC, KD. That's how you multiply, right? But what does S do?
Transpose.
Yep, takes the transpose. So let's take the transpose. And you get KC and KB and KC switch. Any questions? Okay, so now I just do the same thing, but I have the K outside and see what happens. So K, S of A, B, C, D is equal to K times the transpose, which is ACBD. And what's good about that?
It's the same.
Yeah, when you multiply the K through, you get the same thing. So that means that S is a linear transformation. Any questions on that? All right, now let's do the trace. Okay. Okay, and by the way, are real numbers, is that a vector space? What do you think?
Yes.
Yeah, that's a vector space. It's R1. Remember, Rn is always a vector space. That's R1. It's like easy vector. It's too easy to even think about. That's the problem. So we want to say, is this a vector space? What do you think? Do you think it's a vector? I mean, is this a linear transformation? Do you think R is a linear transformation? What do you think?
I don't think so.
Okay, so if you don't think so, that means we're going to look for an example. What do you want to try?
Probably the second is easier.
Huh? The second with a constant?
Yeah.
Okay, so let's try it. What is S of, and actually let's do it in, so it won't be S anymore, it'll be R, but I can copy and paste. In fact, I can copy and paste a lot. So now we're looking at R. What do you want to use for K?
2.
2 it is. What do you want to use for A, B, and C, and D?
I.
Looking for numbers.
I
Oh, yeah, so
didn't.
you want to be 1, 0, 0, 1?
Yeah.
Yeah, I was thinking complex numbers there. Okay. Well, that is R of, that's 2, 0, 0, 2. What's the trace of 2, 0, 0, 2?
That's
4.
4. Any questions on that? Okay, so now let's do the same idea, but now we're going to have the 2 outside. So now we're going to have R 2 times R of 1, 0, 0, 1. So what is R of 1, 0, 0, 1?
That's 4 again. That's 2.
That's 2. What's 2 times 2?
That's 4.
And are we done?
No.
Did we prove that it's not a linear transformation?
No.
No. Did we prove that it is a linear transformation?
No.
Okay, that one didn't work. Okay, can you? Is it because maybe we didn't have a unique enough example, or do you think maybe it's a linear transformation?
I still think it's not the linear transformation.
Okay, then give me an example that's going to make it not work.
Probably we have negatives on the diagonal or one negative.
Okay, how about that? Just like that? I'll let you choose.
Yeah.
Okay, well, if we do that, that becomes negative. And that becomes now 0, right? Do you agree? And that negative one, that 1 becomes negative. The trace of negative 1, 0, 0, 1 is 0. Are we good? Are you happy?
No.
No, that one didn't work either. Negatives didn't help. All right. So do you think it's a linear transformation, or are you still stubborn and think that you can find an example?
No, now that I'm thinking about it, I can't think of a constant that would change it.
Yeah, if you've tried a few and it's not, and they're not going to show you it doesn't work, it's time to try and prove it. Okay. So let's do it in general. And just because I have it here, I'm going to do the second one first. So K, A, B, C, D. And that's equal to KA, KB. Actually, let's do this. So much easier. Wait, it's this one. And what is the trace of K, A, KB, KC, KD?
KA plus KD.
Mm-hmm. All right. And now let's do the same thing. We're going to put, let's just grab these guys. So if we have K of R of ABCD, that's K of, what's R of ABCD?
Let's say plus D.
A plus D.
Which is
that good?
Yeah.
Yeah.
Yeah, that works because that's Ka plus KD by the distributive property of numbers. So we just proved number 2. Okay, and again, it doesn't matter which order you prove them in. So let's go to number 1. And the idea here is we can copy and paste, make it a K instead of an F. An R instead of an S. That S becomes an R. So what is R of A plus E, B plus F, C plus G, D plus H?
A plus C plus D plus H.
Okay, any questions on that? And now let's do the other one. I'm going to copy and paste because it's easier. And that is at this one. So we have R of ABCD plus S of EFGH. Okay, what's R of ABCD?
A plus B.
A plus B. And what's S of EFGH?
E plus H.
E plus H. Are they the same?
Yeah.
Yeah, because remember it's addition. Addition satisfies commutivity, then that's good. So therefore, R is a linear transformation. So I'm kind of glad you guessed it wasn't, because I wanted to demonstrate the fact that don't just say, oh, I tried something and it didn't work, so I'm going to give up. No, you don't give up. You might change your mind sometimes and say, I think maybe it is a linear transformation, and try that. Okay, and that happens. Sometimes your intuition is wrong, Do I have a letter wrong? Yep, that should be D. Thanks. Both of them, actually. Thanks. So sometimes your intuition is wrong, and that's okay. As long as you look at it again and say, maybe my intuition was wrong. Let's try and prove it right, that it's true. Not a problem. It just takes extra time. Any questions on proving something is or isn't a linear transformation?
Does this one has to do something that the eigenvalues are the trace? That
One more
some of
time?
the eigenvalues are the trace.
So what about the trace now?
That this it's a linear transformation has something to do of with the eigenvalues being the sum of the eigenvalues being the sum of it being the trace.
Not
Or
really.
no?
I mean, that's a true statement. The sum of the eigenvalues of trace. This is just simpler. Trace is just an easy thing. Yeah, this isn't about eigenvalues and eigenvectors. Yeah, this is just.
Okay. Yeah, it feels.
Yeah, it just is what it is.
But
Yeah, it's not. There's no AV equals lambda V or anything like that. This is just simple. Okay. So now let's do some theorems. A lot of them. So the first question.
Yeah. Is this for only 2x2 matrices?
For n by n matrices, trace still works. If you look at the proof, if you can imagine 3 by 3, wouldn't it be any different except more writing?
Okay.
So I usually use 2 by 2 just because it's so much easier to type 2 by 2s.
Definitely.
Yeah, so that's my real reason. Not because 2 by 2s are special. They're just specially easy to type. But yeah, I could do 100 by 100, but I'd be here all day long typing them because that's 10,000 entries. No thanks. But yeah, the trace turns out the trace and the transpose are linear transformation for any n by n matrix. And that you would prove with I's and J's and stuff like that, but I'm not going to do it. Okay, so let me talk about the next theorem. It's a nice, easy theorem. If we have a linear transformation from V to W, then, no, it's not number 3. I hate when the computer does this. There we go. Number 1 is T of 0 equals 0. Why is that true? Why must T of 0 be 0?
It's a vector space.
No, it's a linear transformation. On a vector space, but that but there's only 2 things you can use, right? The only 2 things you can use are T of U plus V equals T of U plus T of V, and T of K times V equals KT of V. So which of those are you going to use? Any thoughts?
probably we let K be 0.
Exactly. So we know that T of K V is, we can let K be 0. So we can look at T of 0V. Well, T of 0V is 0. Okay. But T of 0V is equal to 0 T of V. Because linear transformations, you could pull the constant out. But 0 times a vector is 0. There's the whole proof. Isn't that beautiful when you can prove it that fast? Any questions on the proof? Okay. How about number 2? Any ideas?
Doing the same thing.
Similar, not the same. We're not going to put a 0 in there because that just zeroes everything out. But we can go T of negative V equals, it's not going to be 0v. Now what is it going to be?
Negative 1v.
Negative 1v. Right? We had a theorem that that's true, by the way. I know it's just obviously true, but it really was a theorem. That's equal to negative 1 times t of v. And we had a theorem that negative 1 times t of v is negative t of v. That's the whole proof. Any questions on that? I think I'm not going to prove number 3 because this is a lot of typing, but I'm going to talk about it. In one word, maybe 2 words, how would you prove number 3? What's the technique?
Use the definition.
I mean, the definitely part of it, obviously, but thinking about a technique of proof. Any thoughts? All right, if no one's telling me, mathematical induction. So you show it's true for k equals 1, then you say assume it's true if k equals, if k equals n, and then prove that it's true for k equals n plus 1. Okay, I think I'm not going to do that because it takes a lot of time to type, but that's how you would do it. And it just follows immediately. So math induction definitely makes number 3 a proof. True. Any questions on the theorem? Okay, it just says, I mean, most of it's obvious. If you plug in 0, you always get 0. You can pull out a negative, and you can not just split a single plus, but you can split a bunch of pluses. That's all the theorem is saying. You use it a lot, but you usually use it without even thinking. Any questions on this theorem? Okay, next theorem. A lot of theorems coming up. We just did the big definition. I spent a lot of time on the definition because that was the biggie. Now it's theorems about that definition. Okay, so S and T are linear transformations from V to W. And if V is equal to the span of V1 through Vk. Okay, then S equals T if and only if S of Vi equals T of Vi for every I. So what this is saying is that if you know what S does to a basis, basically, or a spanning list, let's say that, we'll get to basis in a bit, a spanning list, then we know what S does for everything. Okay, how do you easily prove this?
Do proofs 1 and 2 for both S and T.
We're not proving these are linear transformations. We're given they're linear transformations.
Hmm.
So you don't need to prove 1 and 2. Does that make sense? We have to prove that S equals T if and only if S equals T for all the individuals. First thing, this is if and only if, but if S equals T, then of course S of Vi equals T of Vi, because S equals T. Because if S equals T, you can erase the S and write a T. That's all that says. Any questions on that? So really the proof is one direction because the other's obvious. So what can we do? Well, what does it mean? What does it mean for S to be equal to T? What do we have to show? Means S of V equals T of V for every V in V. Okay, that's our goal. Let me write goal. Any questions on that? Given this, so maybe I should write given. So that's our goal, is that if S of all the V's are the same, then S is the same for any V. So hopefully you're used to this. When you want to show an equality, start on the left, you end on the right. S of V equals, now what do I have to use? What haven't I used yet?
V1 through VK,
This
Yeah,
part.
but even more, four-letter word,
the span.
span. Okay, so we know that we can rewrite V as the following. We can rewrite V as S. So we can write V as C1, V1 plus dot, 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 plus CK. Whoa. VK. Isn't that what it means for V1 through VK to span V? So now what can I do? Hint, linear transformation.
Pull out the constants.
Pull out the constants and split the pluses, because that's what you're allowed to do with linear transformations. That was the theorem above, right? Okay, so that's equal to C1, T of V1, sorry, S of V1, plus dot, 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 plus CK, S of VK. But we know we're given that S of VI equals T of VI for all of them. So I can take this equation and I could replace all the S's with T's. Any questions on that? Because that's what's given. And now what can I do?
Put it back together and close parentheses.
Yeah, I could put it back together with a T instead of an S, right? But what is C1V1 plus dot, 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 CKVK?
Is the span.
But what is it in one letter?
S.
No, not that letter.
Yeah, it's B.
V. So that's T of V. And I'm done. Any questions on the proof? So that means S of V is T of V for any V. So that means S and T are the same. Any questions on this theorem and the proof? Okay, what this says is that if you know what a linear transformation does to elements of the span, then we know what it does to everything. That's what this says. All right, next theorem says, let's suppose that V and W are vector spaces, and the dimension of V is n. And let's suppose that W1 through Wn are vectors in W. Then there exists a basis V1 through Vk of V and a unique linear transformation T such that T of Vi equals Wi. Okay, so I'll let you read this again because there's a lot of letters here. So I'll give you a second to read through it. And I guess I need, this K might as well be an N. Because if the dimension of V is N, then a basis always has N vectors. Okay. Now, does that mean that W1 through Wn is a basis for W?
No.
No. W may not even be the same dimension. W could be some small dimension, and that's not going to happen. Okay. But what can I do? So how do I make this work?
I have a quick question.
Mhm.
Would this be considered a Jacobian? A unique linear transformation from one vector space to a different one?
Well, Jacobians are pretty specialized, right? Jacobians are partial derivatives, right? They're partial derivatives of a function of multiple variables. So it's pretty different. Where this is more general. Does that make sense?
Yeah.
Yeah, there's no derivatives in this thing.
I guess I just took the word unique, and ran with it.
Okay, yeah. Yeah, the Jacobian has unique in it, but that doesn't mean that this is definitely not the same thing. Okay. But what this does is it says we can do it. Okay. So again, it's unique. Okay, so you have W1 through Wn are vectors in W. Okay. And by the way, they could all be the same vector. They could all be the zero vector for all we know. Okay. But we have there exists a basis for V. That's the key. Okay. And once you pick that basis, then it must be unique. Okay. So first thing is grab a basis for V. That you can always do. Hopefully given any n-dimensional vector space V, there's always a basis for V. So the main thing is once you've selected the basis for V, then this transformation is unique. And why must it be unique? Because that's what we're trying to prove.
Because it's a basis?
Yeah, it's a basis. So we can use the theorem above. A basis always spans V, right?
Yeah.
By definition, right? That's part of basis, right? So that means that what if we know where V1 through Vn goes, where they have to go to W, then we know what T is. Because once we know, then there's only one. Does that make sense? So it's really more of a corollary. The book calls it theorem, but I'm going to call it corollary. Because basically it comes immediately. Oops. Except it's one R and two L's. There we go. It comes immediately from the theorem above. Do you see why it's immediate? Because if you're told where each of the V's go, the VI's go, then you know where everything goes. So we're told the VI is WI. So that means we know where everything goes. That means there's only one choice. And there it is. Any questions on this theorem? Okay, now comes the next section. So we're moving into the second section. And I have a definition that you've already seen before. You just haven't seen it in this thinking. So a linear transformation T from V to W is onto if the image of T equals W. Okay. Have you seen this theorem, this definition before?
Yep.
It's exactly the same. The only difference is the way we think about it. So now we're not thinking of V and W being in Rn. We're just thinking of V and W be general vector spaces. But it's exactly the same wording. And similarly, T is 1-to-1. If T of U equals T of V, implies that U equals V. Have you heard that before? Have you heard of the definition of 1-to-1?
Yeah.
Yeah. Is this any different?
No.
No, other than the fact that T, V, and W don't necessarily have to be in Rn. This works for any any vector spaces. Okay, how about 1 to 1 is equivalent to T of V equals 0, implies V equals 0. Have you heard that before?
Yeah.
Same theorem. So there's really not, do you agree there's nothing new here other than just a new way of thinking about it? So we still have 1 to 1 and onto. We still have 1 to 1 is the same. All you do is focus on 0, and that's good enough. And that works for everything. Then you have everything. So that still works. Any questions on this definition? Any questions? All right, let me just throw some things at you. Is the derivative 1 to 1 onto neither or both? So remember, we're looking at all differentiable functions. What do you think? Maybe I'll type that out. So is the T of F equal F prime 1 to 1 onto neither or both? What do you think?
I don't think 1 to 1.
Yeah, I don't think it's 1 to 1.
Okay. So if it's not 1 to 1, can you think of a function, right? A vector V such that T of V is 0. Hint that's easy.
Any real
I want an example.
1? or
Good.
2?
How about F of X equals 1? Yeah. So it's not onto. Sorry, it's not 1 to 1. Let F of X equal 1. Then clearly the derivative of 1 is 0. So, and 1 is not 0. So it's not 1 to 1. Is that clear? How about onto?
It's possible.
Well, it's either yes or no.
I'm gonna go with yes.
Okay. Why? Why is it yes?
Because if we're going from V to W, and we already know that the derivative is a linear transformation, then the image is going to be in W.
We know the image is in W, but is it all of W? By definition, it's in W, or it wouldn't be a linear transformation. But is it all of W? Is every W hit? Is every vector in W hit by a vector in V? The answer is yes, but you need calculus. So let me write it is onto. Or let's write T is onto. Since, how do you go backwards?
You integrate.
Yeah, integrals. Every differential function is integrable, right? Because the differential function is continuous and continuous functions are all integrable. That came from calculus. So this is an example of an onto function that is not 1 to 1. Any questions on that? Any questions? Okay, let's try another one. How about T of A is equal to A transpose? Same question. 1 to 1 onto neither or both.
I'm gonna say yes to 1 to 1 this time.
Okay. How about onto? Well, let's do 1 to 1 first. Why is it yes? Remember, it's never a guess. It's you have to actually explain why.
Because if we transpose the 0 matrix, we get 0.
It's kind of the opposite of that. If you transpose a matrix and get 0, you didn't start with 0. I mean that you must have started with 0. So if a transpose is equal to 0, then A equals 0. Any questions on that? Okay, if all you did was switch the order of the numbers and you got the 0 matrix, then the numbers must all have been 0. Do you agree?
Yes.
Yeah, that's all that's saying. I mean, it's very simple if you understand it. And if you don't, then it's not simple. But that's all it's saying. If you take a bunch of numbers and you reorder them, okay, you move them from bottom left to top right and back and everything you get ends up being 0, then you must have started with all zeros, because all you're doing is moving the numbers. You're not doing arithmetic on the numbers. How about on to? Yes or no? What do you think?
I think it's on.
Okay, so yes. How come?
Yeah. I guess we can always take the transpose of a transpose and get the
Exactly. Right, we have that as a theorem. So A transpose equals A. So that means that if we have a matrix in W, then we can always take the transpose of that matrix and call that the matrix in V, and its transpose will be the matrix you started with. That's what this says. So in this case, the transpose linear transformation is both one-to-one and onto. Any questions on that? Do you remember the definition that we had about one-to-one and onto?
It's isomorphic.
Mm-hmm. So that's coming. Actually, we got one more theorem first, and then we'll get to that definition about isomorphism. But the nice thing is everything is the same as what we did last time, but now our examples are funkier, right? They're matrices and functions and all kinds of weird things, whereas before it was just Rn. So if T is one-to-one and V1 through Vk is linear independent, then T of V1 through T of Vk is also linearly independent. If T is onto and V is in the span, V is the span of V1 through Vk, then W is the span of T of V1 through Vk. Okay, so that says that one-to-one. So if you have one-to-one, then linearly independent vectors get sent to linear independent vectors. And if you have an onto linear transformation, then that says that if you look at the V as a span of a bunch of vectors, and then you take the linear transformation of those vectors, then they will span W. Okay, I think what I'll do is I'll prove one of them. Which one do you want to see proven?
Onto.
Onto it is. Okay, so proof of onto. So let T be onto. Okay, and V is the span of V1 through Vk. Okay, we want to show that W is in the span of T of V1 through T of Vk. What, do you remember what it means to be in the span? To be equal to the span?
Be a linear combination of a basis.
Yeah, well, of those vectors. They're not a basis necessarily, right? They might not be linear independent, but the point is that every vector in W can be written as a linear combination of these TVI 1 through VK. So what I can do is I can say, let W be in W. So suppose I have a vector in W. Well, T is onto. What does that tell me? What does it mean for T to be onto?
The image of V is equal to W.
Yeah, but I want this little w. That's a hint. I started out. There exists a little v in capital V with T of little v equal W. That's what onto means. Any questions on that? Okay, we're getting there. But capital V is a span of V1 through VK. So how can I rewrite little v?
As a linear combination.
Yeah. So let me just write this out. Since capital V is a span of V1 through VK, we know that T of V is equal to T of, I think I've done it here so I can copy paste, have I? Yeah. T of C1 V1 plus dot 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 CK VK for constants C1 through CK. That's what it means to span. Now what can I do? We've done this before.
Pull out the constants and split the pluses.
Yep. So now we can pull out the constants. And by the way, this was W, was T of V. Okay. So I can pull out the constants, split the pluses, which I think I did up here. So I don't have to retype. Just backwards. So we're done. So that means every W can be written as a linear combination of the T of VKs. Any questions on that? Any questions? Okay. So now the definition, which you should all already know, even though I haven't officially had this definition about general vector spaces, but it is an important one. And that is, if T is 1-to-1 and onto, then T is an isomorphism. We also say V is isomorphic to W if there exists an isomorphism T from V to W. So how about our P3 and M2 by 2 isomorphic. What do you think?
Well, from what you asked us earlier, I'm going to say yes.
Okay, so the answer is you think yes. Okay, it turns out yes. So now we just got to come up with it, and it's really easy. That's the hint. So if we can come up with an isomorphism, then they're isomorphic. Do you agree? So let's do it. All right, what do you think T of, well, something in P3 is AX cubed plus BX squared plus CX plus D. Any guess on what that is? Remember, T is a linear transformation, needs to be from P3 to M2 by 2. So what do you think I'm going to put in here?
The constants.
A, B, C, D. Okay, it's obvious if you just like do it. Do you agree? What else would you do? All right, take a look. Why is this 1-to-1?
Because if we let A, B, C, and D be 0, we'll get
Yeah, so if you start out with, if we have the zero matrix, then that must have come from the zero polynomial because A, B, C, and D are 0. Do you see that? So 1-1 is immediate. Why is it on to?
We can write it as a linear combination.
You're getting a little abstract. It's simpler than that.
because for every P3 we have a matrix.
Actually, it's the opposite. Remember, it's for every matrix. So it's for every matrix, you have a P3 is what you need. That's on to.
Okay.
So for every matrix, A, B, C, D, whatever numbers A, B, C, and D are, just plug in AX cubed plus BX squared plus CX plus D. And guess what? You'll get that matrix. There's nothing to it. Do you agree?
Yeah.
So the answer is yes. So P3 and M2 by 2 are isomorphic to each other, even though they don't feel the same at all, do they? Polynomials, some kind of curvy thing in the XY plane versus matrices, do they feel like they're the same things?
They don't feel like it.
But they are. Okay, at least they're isomorphic. Given one, you get the other. Okay, any questions on that? Okay, again, you just got to get used to weirdness, and once you get used to weirdness, it's not weird anymore.
So is this for any polynomial of degree n or less?
Will be M2 by 2.
No, but matrix of some sort.
Sure. You could always do a 1 by n matrix, or n plus 1, I guess. And if it happens to be, if n plus 1, if you're looking at Pn, if n plus 1 is not prime, then you can write it as a matrix that isn't just a 1 by something. Does that make sense?
Yeah.
Yeah. So it's not only, so for example, P5 is isomorphic to M2 by 3. It's also isomorphic to M6 by 1. It's also isomorphic to M3 by 2. Do you see that?
Yeah.
Because you just position the A, B, C, D, E, F. You just put them together. Does that make sense? You do the same thing. Yeah, that always works. And we'll get a theorem about that in a minute. All right, so now some more theorems. So let S be an isomorphism from U to V, and T be an isomorphism from V to W. Okay, T inverse is an isomorphism from W to V, and T of S is an isomorphism from U to W. Okay. What this says is if you have an isomorphism that goes from left to right, then take the inverse, go from right to left, it's still an isomorphism. Does that make sense?
Yeah.
So it's kind of if P3 is isomorphic to M2 by 2, then M2 by 2 is isomorphic to P3. You just go backwards. And similarly, P3 is isomorphic to M2 by 2. M2 is isomorphic to R4. So that means that P3 is isomorphic to R4. That's what this T of S is. It means just kind of move and then move again. And as long as you're 1-to-1 and onto, you do it twice, you're still 1-to-1 and onto. Any questions on that? Okay, we don't have so much time, so I can't prove everything, but at least I could say examples. So example, we know that P3, actually, let's do this so you don't have to retype. So P3, let's write it this way, is isomorphic. Whoa. To M2 by 2. We just proved that. And M2 by 2 is isomorphic to R4. You believe that? How would you, what would you use for the isomorphism? And the hint is it's really easy and obvious. Where would the matrix ABCD go? If you want a 4 vector. The hint is it's really obvious and easy. I don't hear you jumping in, so maybe I'll do it. So let's say S of the matrix ABCD is equal to what?
R4.
Right. But we need to say what vector in R4 is it going to be?
Oh,
It's obvious.
X, Y, Z, W.
No, easier. Where is S going to take the matrix ABCD? Can take it to A, comma B, comma C,
Yeah.
comma D. I mean, do y'all agree that's obvious?
Yeah.
There's nothing there. You just read it, but you read it not thinking as a matrix, you read it thinking of as an R4. And that's an isomorphism. So what that tells us, since I got an isomorphism from P3 to M2 by 2, and then I got an isomorphism from M2 by 2 to R4, that means that P3 is isomorphic to R4. So you can get rid of the middleman. Any questions on this example? Okay, more theorems. We have enough time, I think. We don't have too many left. So if T is an isomorphism from V to W, and V1 through VK is a basis for V, then T1 through TK is a basis for W. Why is that immediately true from what we've already done? What 2 things do you need for a basis?
Linearly independent and span.
Right. And remember, we had a theorem already that did this. Right? T is 1-to-1, VK 1 through VK linear independent, then T of V1 through VK is linear independent. Okay, by the way, if T is onto and we got a span, V is the span of V1 through VK, then W is the span of T of V1 through T of VK. So it just says that if you have both linear independent and span in the domain, then you have both linear independent and span in the range. Because the theorem says it one at a time, and the theorem I just mentioned says it together. But it doesn't matter whether you say it one at a time or together, it's the same thing. Any questions on this theorem? Okay. So again, there's not much to say about it because it's just a restatement of the other theorem. Okay, if V and W are vector spaces, then V is isomorphic to W. This is really important. If and only if V and W have the same dimension. So notice in these examples, the dimension of P3 is 4. The dimension of M2 by 2 is 4. Dimension of R4 is 4. It's not a coincidence. Okay, so if the dimension is 4, then it's always isomorphic to P3, for example, no matter what you started with. Okay, why is that true immediately? Why is the theorem an easy one also? What's the definition of dimension? What does it mean for V to have dimension n?
Well, that means that in the basis of V, there are n linear independent vectors.
Exactly. So if dimension of V equal n, then the basis for V has n vectors. But then T of those bases, let me write this down. Okay, then T of those vectors must be a basis for W, right? So that means they're isomorphic because we just found the transformation. So you just and I guess you should say T of V1 equals W1. And T of VK equals WK. You can always just do that. So we can just do that, and that's a linear transformation that is 1-to-1 and onto, right? Because if a basis goes to a basis, it must be onto. If you hit all the basis vectors, you're onto. Any questions on that? And again, if you have the same dimension, you better be 1-to-1. So if you didn't have the same dimension, you wouldn't have enough. So that tells us that every vector space of dimension 5, for example, is isomorphic to every other vector space of dimension 5. Isn't that beautiful? So here's a nice thing. Here's a corollary, which the book doesn't write, but it should. Maybe it does in another section. I always do the wrong number of letters. 2 else. So corollary is every finite dimensional vector space is isomorphic to Rn, where n is the dimension of the original vector space. So what is M4 by 5 isomorphic to?
It's R20, right?
Yep, R20. Isn't that easy? Okay, what is P7 isomorphic to?
R8.
Yep, R8.
Or
Okay, isn't that wonderful? This always works. Okay, so if all you care about is isomorphic, that means all that stuff we did with Rn is good enough. That's all we need because everything is isomorphic to Rn. Okay, everything that's finite dimensional. Are there vector spaces that are not finite dimensional?
Probably.
Yeah, which one? I've talked about them. Give me an example.
the real,
What's that?
all the reals.
Real numbers is one dimensional.
Infinity.
We've had a bunch of examples today, actually, a few. Okay. The vector space of all differential functions is not finite dimensional. Right? The vector space of all functions is not finite dimensional. So the functions are the biggest, most common example of not finite dimensional. Any questions on that idea? Oh, what just happened?
Is that because there's an infinite number of differentiable functions?
Well, it's not just that, because say there's an infinite number of polynomials degree 3 also. It's because if you write the power series, you're never going to get a higher enough degree for e to the x, for example. That's kind of one of the ways of looking at it, right? That has an infinite set of functions to make that power series happen. I think I'm not going to get into that because I got a little left to do. I want to do this one. I only have 2 minutes left. But the good news is I could do this in 2 minutes. So if V and W have the same dimension, and T is a linear transformation from V to W, then the following are equivalent. Okay. This is not, by the way, the main TFAE theorem that we've had in the past. This is its own little following are equivalent. T is 1-to-1. T is onto. T is an isomorphism. Okay, so that's a major theorem. And what it does is if you want to prove that a linear transformation is an isomorphism from V to W, and you know V and W have the same dimension, it means you only have to do half the work. 1-to-1 and you're done. And 1-to-1 is usually the easiest. So it says that all you need is one of those and you got the other. Okay, I don't have time to prove the theorem because we only have 1 minute left. But are there any questions about this particular theorem? Right, 3 implies 1 and 2 immediately because that's the definition of isomorphism, 1-to-1 and onto. So what's interesting is that 1 implies 3 and 2 implies 3 by themselves, as long as the dimensions are the same. Any questions at all about this theorem? Okay, it's 2:45, so I'm going to stop the share. And we don't have a lot of lectures left, by the way. So weird to still have to be online. Next year we'll be face-to-face, I'm pretty sure. You'll be out in a university, but I'll be face-to-face with new students. So I'm going to stop the recording.